Last time we discussed about the Schrodinger's wave equation. Now in this section let us discuss about the application of Schrodinger's wave equation for a given particular problem. So we want to give an example for how the quantum mechanics runs with the help of the Schrodinger's wave equation. For that we have taken an ideal simple case of a particle in an infinite potential well, or also called as the rigid box. Let us first define what is this potential well. So we have taken here only one dimension also, that is only the particle moving along x-axis. So along the x-axis between x equal to 0 to x equal to L, the potential field is 0. And as soon as you come to x equal to 0, the potential becomes infinite and beyond also. The same thing on the other boundary, x equal to L as well as beyond that, the potential is infinite. So particle of mass m moving with velocity v is considered here within this region between 0 to L, where the potential is 0. Now we have to see how the Schrodinger's wave equation can be applied to this. So you can see here the particle is always trapped inside this region and is not able to get into the other region here because the potential becomes infinite. So for region x equal to x less than or equal to 0 and x greater than or equal to L, that is outside the potential well where the potential is infinite, the wave function psi is 0 as particle cannot be existing at the walls and beyond. Now let us take the case of 0 less than x less than L, where the potential is 0. So start with the Schrodinger's wave equation, which is d square psi by dx square plus 8 pi square m by h square into e minus v into psi is equal to 0. So this is the Schrodinger's equation we have to start with, and substitute here the potential value v equal to 0 in this equation, and then we get d square psi by dx square plus 8 pi square m e by h square into psi is equal to 0. So here I will take this part as a constant part, that is k square equal to 8 pi square m e by h square. So then I can write this equation as d square psi by dx square plus k square psi is equal to 0. So this is the second order differential equation in one of the standard form that is used in mathematics. The general solution for this kind of a second order differential equation is always given by this: psi is equal to a cos kx plus b sin kx. So this is the general solution with the values here a and b. These are the arbitrary constants. Arbitrary means they can take any value and yet they will be at this function will be a solution of this second order differential equation. That's why it's called as the general solution. So we have to get a particular solution from this. For that we have to apply the boundary conditions related to the given physical problem. Now the boundary conditions for the given physical problem can be defined like this: at x equal to 0 at one of the boundary, the wave function psi is 0 because the potential is infinite, so particle cannot come to this point x equal to 0, therefore psi becomes 0 at x equal to 0. So substitute this boundary condition to the general solution, which is psi is equal to a cos kx plus b sin kx. So x equal to 0 we substitute here, then cos 0 it becomes, which is 1. So we have 1 into a plus b sin kx. So substitute x equal to 0 here, so it becomes sin 0, but sin 0 is 0, so 0 into b 0. So we have therefore a plus 0 is equal to psi on the left hand side, but psi is also 0 at this x equal to 0. Therefore a becomes equal to 0. So applying the first boundary condition, we see that the constant a becomes 0. Now apply the second boundary condition: at x equal to L, psi is 0. So at the second boundary also, the other boundary also, the wave function becomes 0 because the potential is infinite. So substituting this again in the general solution, we now have b sine kl, x is L, so b sine kl plus a is already 0 here, so this part is 0, is equal to psi is 0. So therefore we get b sine kl is equal to 0. So here we have to note that b cannot be 0. Already a is 0 in the general solution. If b is also 0, then the wave function becomes 0. That means the particle is not present, which is not true. Therefore we cannot take b to be 0, so it must be therefore sin kl 0. So sin kl is 0, therefore kl must be equal to n pi, or k is equal to n pi by l. So therefore the general solution now becomes equal to psi is equal to b sine of n pi x by l, where we take n to be 1, 2, 3. Actually mathematically n equal to 0 is also allowed for this, but we have taken n equal to 0 as ruled out case. This is because if I take n equal to 0, again it becomes sine of 0, which is 0, the wave function becomes 0. But in the given region the particle is present, so wave function cannot be 0. Therefore we take n equal to 0 as ruled out case. So therefore we start with n value as 1, 2, 3, so on. So this is the particular solution we get. Now let us take the equation 1 and 3. So equation 1, we took k square is equal to 8 pi square me by h square, and equation 3 we got k is equal to n pi by l. So in both the equations we have k as the common term. Therefore if we equate those two equations, we get k square, which is 8 pi square me by h square, is equal to, so k from this third equation is we can write it as k square as n square pi square by l square. So here pi square can be cancelled out, and rewriting this we get the energy term En is equal to n square h square by 8m l square. Again the n value starts from 1, 2, 3, so on. So these are the values for the energy of the particle in the given potential well. These are called as the energy eigen values. So we see here that the energy the particle can possess is not continuous in nature, but it is discrete in nature, specified by this quantum number n is equal to 1, 2, 3, so on. So if I put n is equal to 1, the lowest value we get for the energy, so we get E1 is equal to h square by 8m l square. So this is called as the ground state energy, or also called the 0 point energy. So it's a small value but still not 0. So this is what we find in quantum mechanics. The lowest value the particle can possess is non-zero. The next value of energy the particle can possess is obtained by putting n is equal to 2 in this equation. So you get 2 square, that is 4 times. That means the next state, we call it as the first excited state, is equal to 4 times the ground state energy. Similarly, if we put n is equal to 3, we get the second excited state, and the second excited state energy is 9 times the ground state energy. So this is how we get the discrete energy values for the particle in the potential well. Now the example for this is the general case of an electron in the atom. So it is similar to the particle in the potential well, and therefore we see that the electron in an atom should have discrete energy levels, which is what we saw in the Niels Bohr atomic model. Now let us see the normalization procedure which we have to do for the particular solution which you obtained. So you got the particular solution psi is equal to b sine of n pi x by l. But according to quantum mechanics, this wave function is not yet ready to use. We have to calibrate it or normalize it. So normalization procedure is done first of all with the probability density function, which is psi into psi star or mod psi square. So you have to take the wave function psi and multiply with the complex conjugate. So wave function psi is this. What is the conjugate, complex conjugate of this? So complex conjugate of this is same function, because it's a pure real function with no imaginary part. Therefore psi star is also same function. So multiply these two, we get mod psi square. To do the normalization, we have to take the integral of mod psi square dx over the given region. The given region is nothing but the potential well from x equal to 0 to x equal to L, where the particle is present. So take the integral of the mod psi square, which is b square sine square of n pi x by L dx between the limit 0 to L. Now to find the integral of sine square of theta, we can use the formula, that is sine square theta can be written as 1 minus cos 2 theta divided by 2. So applying that here, we get sine square of n pi x by L is written as 1 minus cos of 2 n pi x by L whole divided by 2, that I have taken outside here along with another constant, that is b square. So you get therefore b square by 2 integral 0 to L of 1 minus cos 2 n pi x by L dx. Now find out the integral of this. Integral of 1 is x, integral of cos of the some function, cos of some value is sine of that value divided by the coefficient of x, which is 2n pi by L. So therefore we get b square by 2 and apply the limits, that is the lower limit 0 and upper limit L. We get b square by 2 L minus this term, when you apply the upper and lower limit, it becomes 0 for both the limits. Therefore we get L minus 0. So this is the value we get here, which we can now call it as equal to n square. According to normalization procedure, the integral value whatever we get, we call it as n square, and from that find out what is n. So n is square root of this, which is b into root of L by 2. Now the normalized wave function psi n is obtained as psi n is equal to psi divided by n. So psi is the original function, that is the particular function which you obtained, that is b sine of n pi x by L, divided by this n here we obtained is b root of L by 2. So here b gets cancelled, therefore we get the normalized wave function psi n is equal to root of 2 by L sine of n pi x by L. The values of n start from 1, 2, 3, so on. So these are also called as the Eigen functions. So this is the normalized wave function now, which is ready to give us the information about the particle in the given potential well. The information we can extract from this are like what are its energy values, what are the probability functions, where the maximum chance of finding the particle is possible in the given potential well. So all those things information can be obtained from this the normalized wave function or the Eigen function. With the help of the operators, when we apply the operators on this wave function, we will be able to extract information from that, and those information which you obtain are called as the Eigen values. Having discussed the normalized wave function for the particle in the one-dimensional potential well, now let us see what is the information we obtain using this normalized wave function about the particle in the potential well. So for this we take the wave function psi n, and from that we can find out what is the probability function p of x, which is given by mod psi n square, which is psi n into psi n star. Psi n is the wave function, psi n star is the complex conjugate, which we get here is like this 2 by L sine square of n pi x by L. So this is because the given wave function psi n is purely real function with no imaginary part. Therefore mod psi n square is simply square of this function. Now let us see how this works out for different values of the quantum number n as well as the different position of the particle in the potential well. Let's start with n is equal to 1, the lowest energy level, the ground state. So we have to put here in the wave function n is equal to 1 as well as in the probability function n is equal to 1. So if I look at the probability function n is equal to 1, then it becomes p of x is equal to mod psi n square is equal to 2 by L sine square of pi x by L. Now if I put x is equal to 0 here, then we see that this becomes in the wave function also, if I put x is equal to 0, then the wave function becomes 0. At x, the probability function also same thing becomes 0 here, because we put sign of 0 is 0. And x is equal to L if we put here, and both in the wave function as well as the probability function, if I put x is equal to L, then it becomes sine of 1 pi. So that is 0. Here also if I put in the probability function x is equal to L, it becomes sine pi, which is 0. So both at the x is equal to 0 and L, the wave function is 0 and probability of function is also 0. So this is an obvious case which we already discussed. Now let us see at the other point, say x is equal to L by 2. So put x is equal to L by 2 here, and we see that we get sine square of pi by 2, and we know that sine pi by 2 is 1, which is the maximum value. The same thing is true for the wave function also. We get sine of pi by 2, which is maximum. So we see that the wave function psi1 is maximum and the probability function p of x is also maximum for the n is equal to 1, the ground state. Now let us represent here with the help of the graph here. So I have got two graphs here, one for the wave function psi and another for the probability function p of x. So here we have taken the potential well from x is equal to 0 to x is equal to L, and this is the ground state n is equal to 1. So for the wave function it is 0 at the two boundaries, and it goes increasing like this and becomes maximum at the center. Now if I look at the probability function, it is again we see that x is equal to 0 and x is equal to L, the probability function is 0. But as you go toward the center, the probability of finding the particle increases and becomes maximum at the center. And as you go away from the center toward the other boundary, the probability again decreases and becomes 0 at the other boundary. So the maximum chance of finding the particle is in this region at the center, when the particle is in the ground state. Now let us analyze similarly for n is equal to 2, the first excited state. So if you take the wave function, then the wave function for the first excited state becomes psi2 is equal to root of 2 by L sine of 2 pi x by L. By substituting for n is equal to 2, you get this. Then probability function p of x is equal to mod psi2 square, which is equal to 2 by L sine square of 2 pi x by L. Now again analyze this for different values of x. If I put x is equal to 0 and x is equal to L and also x is equal to L by 2. So you can see that here in the two functions, 0 it becomes sine 0, x is equal to L, then it becomes sine of 2 pi which is 0, L by 2, then we get again sine of pi which is 0. So wave function is 0. Similarly probability function p of x is also 0. So what we see here is that in the ground state we said that at x is equal to L by 2 the probability of finding the particle is maximum. But we see here when it comes to the first excited state, in this energy level the probability of finding the particle at the center is 0. That means the center becomes the forbidden region for the particle. Now let us see at some other points, say x is equal to L by 4 and 3L by 4. When you put x is equal to L by 4, it becomes sine of pi by 2, which is maximum. If we put x is equal to 3L by 4, then this becomes sine of 3 pi by 2, which is also maximum but negative value. So same thing is true for probability function. For L by 4 this becomes maximum, and also 3L by 4 also it becomes maximum. You have square here, so no negative value, both will be positive. Now represent this in the form of graph here. So you have got here another curve for n is equal to 2, the first excited state. For the wave function psi, it becomes 0 at the two boundaries, x is equal to 0 and x is equal to L, it is 0, and x is equal to L by 2 also the wave function is 0. But how the wave function goes, it goes like this, becomes maximum at L by 4, then again here decreasing to 0, and then on the negative side it becomes maximum at real by 4 and then towards 0 again. So this is the wave function psi. Now let us look at the probability function p of x for the first excited state. So n is equal to 2. For that we see that the probability function becomes 0 at the two boundaries and also at the center of the potential well, but the probability of finding the particle becomes increasing as you go towards the other side. That becomes maximum at L by 4. Again after L by 4 it starts to decrease towards 0 at the center, and again it goes increasing towards maximum at 3L by 4 and then decreases. So this is the probability function for the first excited state. So here we see that the probability of finding the particle at the center is 0, whereas for the ground state the probability of finding the particle was maximum here. So this is the important difference we find, and this is what we say in the modern physics as the forbidden region for the particle in the atom, like electron in the atom. Now same way we can go on for other energy levels like n is equal to 3, the second excited state, and so on. So this is how we are able to discuss about the particle in the one dimension potential well using the normalized wave function which you obtain using the Schrodinger's wave equation.